and you'd like to present Professor Toshihiko Ota. That is an accomplished researcher specialized in the field of elementary particles, phenomenology, cosmology, astrophysics, with particular focus in the nature of neutrinos. He asked me to be very short in the presentation, so he works in different institutions, very prestigious institutes in the world, and now he joined in 2023 in the University of La Serena. Okay, he will talk now about new parameter regions in sterile neutrinos searches, a scenario to alleviate cosmological neutrinos, mass-bound, and its testability oscillation experiments. I'm sorry, my glasses have them some.
Sorry for my long title. Yeah, yeah. First of all, I'm very sorry for my delay. Maybe you expect that the Japanese are punctual, but I was not. Maybe I have been too many years in the outside of Japan. I lost some Japaneseness maybe, but I should not excuse such things. I just straight apologize. I'm very sorry for that. In this talk, I would like to discuss a scenario to relax the cosmological neutrino mass bound and the testability of that scenario at the neutrino oscillation experiment. And then, as an introduction, let's have a look at the current status of neutrino mass measurements. And maybe as you know that the cosmological observations are start putting the stringent constraint to the sum of the neutrino masses. And for example, the combined analysis of CMB measured by Planck and BAO, baryon acoustic oscillation, set the bound to the sum of the neutrino masses at the level of 0.1 electron volt. So the cosmology tells that the sum of the neutrino masses should be smaller than 0.1 electron volt, something like that. And then the lab neutrino experiments also place the bounds to the neutrino masses, but the different combinations of masses and mixings. For example, the neutrino-less double beta decay experiment sets a bound to this combination that is so-called the effective neutrino mass. And the interesting feature of this quantity is that this guy is sensitive to the combination of the Majorana CP phase that cannot be measured in the oscillation experiment. And then the precision measurement of the beta decay spectrum sets a bound to this different combination of the masses and mixings. That is sometimes called the kinetic mass of the electron neutrino. And the Kathleen experiment updated last year their result, and this combination now should be smaller than 0.45 electron volt, something like that. And then neutrino oscillation experiments are not sensitive to the absolute value of the neutrino mass. They are only sensitive to the mass differences, mass square differences. And then the current situation of the neutrino mass measurements may be summarized in this plot. So the horizontal axis is the sum of the neutrino masses, and the vertical axis is the effective neutrino mass. So the cosmology sets a bound from right, and the neutrino-less double beta decay sets a bound from above. I have to say that these two bands, the blue and red, are the two sigma allowed regions in the standard 3-generation neutrino framework after the global fit of the oscillation experiment results. There are two choices for the mass ordering corresponding to the atmospheric neutrino oscillation. And one is a normal ordering, and the other is inverted ordering. And we have still two choices. Yeah, the oscillation experiments tells that the preferred a little bit that normal ordering case, but the difference is less than 2 sigma, so that we still have these two choices, inverted ordering and normal ordering. And here,
because I did this plot, and there are some problems. There is a tension between nova and decay.
yeah,
In inverted ordering, no, in normal ordering.
Uh-huh.
In inverted ordering, there is not a tension.
mhm,
But all the reactors prefers normal ordering. And as you say, the long baseline interference prefers normal ordering. So all the experiments prefers normal ordering unless the tension between decay and nova. So when you combine all these experiments, the tension between nova and decay that prefers inverted ordering against all the other experiments, you cancel out everything,
yeah,
all the preference for normal ordering, and you have not any preference for any ordering.
you are
Summing all the experiments of the field.
You are right. You are completely right. So the no one T2K have the tension, and yeah, and to get to resolve, try to resolve the tension, then we have to go to the inverted ordering, and yeah, you are right. Other things are preferring the normal ordering, but yeah. So you are right, and the situation is so that we don't know the ordering. That's the situation. Yeah. So we have two choices. Yeah. So here is a incomplete list of the experiments that are relevant to the Newton mass measurement. And in near future, once the long baseline neutrino oscillation experiments, next generation long baseline neutrino oscillation experiments, T2 hyper K or Dune experiment will start, then they will soon tell the blue or red, so that they are sensitive to the mass ordering. And the neutrino-less double beta decay experiments will be upgraded, and they are expected to go below this blue band, yeah, in the next end of the next decade, maybe. And yeah, but the interesting thing is that the cosmological observation, they are very strong, and they can maybe in near future they can completely exclude the parameter region of the standard 3 generation neutrino framework. Yeah, this red band and here, and the cosmological, the expected sensitivity of the cosmological observation go beyond that. So the cosmology maybe in near future kill the standard 3 generation neutrino framework. That's a little bit concerning situation. And last year, DESI collaboration released their first result about their measurement of the baryon acoustic oscillation, and the combined analysis of the Planck CMB measurement and this new BAO measurement set the bound to the sum of the neutrino masses at 0.07 electron volt. That is still within the standard 3 generation neutrino framework, but with normal ordering. But what a little bit concerning thing is that the best fit region is the massless neutrino. So if this tendency continues, then the cosmology soon will kill the standard 3 generation neutrino framework. And then I have to say that this combined analysis contains not only the CMB by Planck, but also not only the CMB by Planck and the BAO by DESI, but also the CMB lensing data by the Atacama Cosmology Telescope. So the Chilean contribution is here. And yeah, there are many papers about this concerning situation, and one of them is this. And the title is "No News is Good News," but they are not saying that no neutrinos are good. So that they are saying that no neutrino masses are good for cosmological observations. That's we have seen in the previous slide. So that DESI already said that, but they did their own analysis, and they also find, okay, the massless neutrino is preferred by CMB plus BAO. but they go a little bit beyond. So that if we allow the neutrino can have the negative neutrino mass, then the best fit region actually lies in the negative mass region. Okay, that sounds super nonsense. So that's yeah. But they are not talking about the tachyon or particle moving faster than light or something such thing. They are just saying that they found in the data the enhancement in the small scale structure. In short, when you put the positive neutrino mass in the standard cosmology and do the simulation, then you find that the suppression in the small scale structure. But in the data, there actually is an enhancement we need. So, and then they parameterize that enhancement as a negative neutrino mass, so that it's just a parameterization of the enhancement of the small scale structure. But anyway, so something unexpected is happening in neutrino or in cosmology. Yeah, and there are many discussions. Maybe that is just a tension between some data sets. Some data sets have some problem in the measurement, and because of that, some strong tension. That tension makes that strong bound to the neutrino masses. Someone said that. And the other people say that maybe that we should not handle the neutrino mass bound in the standard cosmology, lambda CDM, because we already know that the lambda CDM has a problem, so that many years we are discussing the Hubble tension, etc., etc. So that we should handle the neutrino mass in the framework of the extended cosmology, not the lambda CDM, maybe. And also, recently the people start talking about the evolving dark energy. Yeah, the recent DAISY data release suggests maybe the cosmological constant is not constant. They're changing in time. But even in such a model, so that even taking this best fit changing cosmological constant, cosmological dark energy model, the best fit point of the neutrino mass is outside of the standard 3 generation framework. So that the boundary is relaxed, but still there is a kind of tension in the neutrino mass measurement. Yeah, so the situation is a little bit concerning, but I'm not a data analyst and I'm not a cosmologist, so I'm a particle phenomenologist. So that in that situation, the question I got is that, is there any particle physics model that save this situation by relaxing the cosmological bound, yeah, cosmological bound to neutrino masses? And actually this question was already asked by these two people, the Yasaman Farza and Sten Hannestad, 10 years ago. So I would like to introduce their scenario. Yeah. Here I take the plot from the paper by the other people, so the Escudero, Schubetz, and Carbo, to illustrate how this mechanism relaxes the cosmological neutrino mass bound. Here I plot the number density of a particle, number density of neutrinos, as a function of the temperature of the universe. So the left end is hot and the right end is cool. And here is MEB, and here is electron volt. So the Big Bang nucleosynthesis happens in this end, and the recombination happens just after this end. And cosmic structures form in this pink region. Yeah. And then in the standard cosmology, nothing happened after neutrinos. Nothing happened to neutrinos after they decoupled from thermal bath. So they just cooled down as universe expands. Yeah. So, and the number density stays at, here the number density is plotted as a ratio to the standard model value, so that that stays at 1 by definition in the entire history of the universe. Then this Farza and Hannestedt scenario, they introduced a new interaction between a pair of neutrinos and a new boson field, X boson. And they assume that the X boson has a mass around kilo electron volt. And also they assume that this X boson interact with a pair of new massless fermion fields. And they introduced the n-chi generations of n-chi copies of massless fermion fields. And then what happened? Just after the Big Bang nucleosynthesis, it's the same as the standard cosmology, but when the temperature drops and the temperature gets close to the mass of the X boson, then the X bosons are started being produced through the neutrino pair annihilation. And then the number density of neutrinos start decreasing because the neutrinos are consumed to produce the X boson. And then after that, the temperature drops more, and then the X boson disappears from the universe. And then that X boson decays dominantly to the chi field, the massless chi field, because they assume that the coupling to the chi field is larger than the coupling to the neutrinos. Then after everything happens, and we have that mixture of the massive neutrinos and the massless chi field. And the cosmological observation, that cosmic structure formed here, so the cosmological observation are only sensitive to the mass of this mixture. And then the cosmological bound to the actual neutrino mass is relaxed, right? So that's the essence of this scenario. And then when we introduce more generations of chi field, then we can dilute more so that we can relax more. That's the idea. Nice. And then these people in 2023, they discussed particle physics realization of that scenario. So they introduced the NS generations of massless sterile neutrinos, and that mass sterile neutrinos are the standard model gauge singlet, but they have the new gauge interaction, new U1 gauge interaction with the new gauge boson Z prime, so that these sterile neutrinos are the chi field in the original scenario, and this Z prime is the X boson in the previous slide. And then these people assume that the sterile neutrino can communicate with the active neutrinos through the mixing, and they assume that this mixing is the flavor universal just for simplicity. But anyway, so now the active neutrinos also can interact with this Z prime boson, X boson. Yeah, now we have all the setup for the Farza and Hannestedt mechanism. And then there are only 4 parameters in this model. So the number of generations of sterile neutrinos, NS, and the mixing, theta S, and the gauge coupling ZZ prime, and the mass of the Z prime, so the MZ prime. So there are only 4 parameters, and they discussed the parameter regions where the Farza and Hannestedt mechanism works, and at the same time various cosmological bands are avoided. And here's a plot of the parameter space MZ prime and ZZ prime, and here the mixing is fixed at 10 to minus 2. And this plot barely depends on the number of generations. And I don't see the line here, but anyway, so that above this orange region, that mechanism works, we can relax the cosmological neutrino mass bound. But green and blue, and here there's a line here, and the gray region already excluded by the different cosmological observations. But there's a room here. There's a room here, actually, the line here. So that in this region, that we can relax the cosmological neutrino mass bound, and at the same time, the various cosmological bounds are avoided. Yeah, the interesting thing is that when we take that mixing too large or too small, then the combination changes. The combination that changes, and that window closes. So we have to have to use this mechanism. We have to have that the active sterile mixing with this size, the 10 to minus 4 to 10 to minus 1. And the interesting thing is that the active sterile mixing with a size of 10 to minus 2, 10 to minus 1 are the target sensitivity reach at the oscillation experiments for the sterile neutrino searches. So we have a chance to test this scenario at the lab oscillation experiment, at least the part of the parameter space. Yeah, so now we are interested in the lab experiment, lab oscillation, oscillation experiment searches for the sterile neutrinos. Yeah, and then in the context of the lab experiment searches, the sterile neutrinos are often or always assumed to be heavier than the active ones. Yeah, this I said that the sterile normal ordering case. Yeah, this normal ordering is nothing to do with the normal ordering I showed in the previous slide. So I am just mentioning here that sterile neutrinos are heavier than the active ones. That this mass pattern. Yeah. In the context of the sterile neutrino searches, the people are always assuming this pattern. But to use the scenario proposed by Falza and Hannestad to relax the cosmological neutrino mass bound, we need the massless sterile neutrinos. So the sterile neutrinos are lighter than the active one. So we want to have this situation. But people are not thinking about this situation. But why? Of course, there are reasons. First of all, the lab experiments are basically sensitive to the mass square difference with the size of electron volt square, because they are interested in the sterile neutrinos to solve the LSND anomaly, or simply the experimental setup. The baseline lengths and the energies are tuned to that mass square difference. So people are interested in the sterile neutrino with a size with the mass square difference with the size of electron volt square. And so that this mass difference at the electron volt, something like that. Then in this inverted ordering case, the active ones are have the mass around the electron volt, and then the cosmological bound set the bound to the sum of the active neutrino masses, and then in this situation the sum of the active neutrino masses is something around the electron volt, and that is in the strong tension with the cosmological observation. As we have seen in the very first slide, the sum of the neutrino masses should be smaller than 0.1 electron volt or something like that. So it's a strong tension, so that people don't think about this situation, and people are thinking about only this situation. But now we are introducing this massless sterile neutrinos to relax the cosmological neutrino mass bound. So that with that relaxed bound, this possibility may be allowed. So then we should think about the lab experimental search of the sterile neutrino with this type of mass pattern. Yeah, why not? But in the short baseline neutrino oscillation experiment, actually that inverted order, sterile inverted ordering case, the sensitivity to the inverted sterile inverted ordering search is the same as the normal ordering, because the oscillation probability is just proportional to the sine square of delta m square, so that it's the same. But the interesting thing happened in the atmospheric neutrino observation at the ice cube experiment. Here the matter effect comes in, so that we have to think about the interaction between the neutrinos and the Earth's matter, and the MSW resonance happens, so that that differentiates the normal ordering case and the inverted ordering case. And here I take the page from the global analysis of the sterile neutrino searches, and it said that the active to sterile neutrino oscillation in matter are resonantly enhanced by the MSW effect. And when you take the mass square difference 1 electron volt, then the neutrino, atmospheric neutrino with the energy of 5.3 TeV is enhanced. The signal is enhanced. Yeah, and they also said that in the normal sterile normal ordering case, as considered in this paper, the resonance is in the anti-neutrino sector. And they also said in the footnote for the inverted ordering case, the resonance would occur for neutrinos, and the signal would therefore be stronger. So the cross-section for neutrinos is larger than the cross-section for antineutrinos. So the signal enhancement effect actually gets stronger in the inverted ordering case. So that's interesting. However, they didn't think about that because of the tension with cosmology. But now we are talking about the relaxation of the cosmological bound. So we should check that. Yeah. And they didn't discuss that. And the IceCube collaboration also didn't study about the inverted ordering case, so we did it. Yeah, so this is the expected sensitivity of the at the IceCube experiment to the inverted ordering sterile neutrinos. Yeah, and actually that the sensitivity is better than the normal ordering case. That is the dashed curve. So we show that the IceCube is actually the good tool to explore the parameter region for this scenario. So that's the best way to explore the parameter region of this scenario. But to open up the parameter region up to here, where the IceCube experiment sensitive to, we have to introduce, so we have to relax the cosmological neutrino mass bound up to here, corresponding to this mass square difference. To do that, we need to introduce the 50, 60, 70 generations of massless sterile neutrinos. That's a little bit sounds too radical, maybe. Yeah, it's technically no problem, but sounds really such 50 sterile neutrinos. That's a little bit too much, maybe. So instead of giving the summary and conclusion, I would like to discuss two other physics cases, not so radical one. Yeah, the first case is suppose in near future that if the Catherine experiment find the signal and the kinetic neutrino mass is at the 0.2 electron volt, and suppose the neutrino-less double beta decay will be discovered, yeah, at 0.1 electron volt, then they are consistent with each other in the standard 3 generation neutrino framework but they suggest the sum of the neutrino masses should be 0.6 electron volt. That is in strong tension with the cosmological observation, but we can relax that cosmological bound by introducing 20 massless sterile neutrinos. Yeah, that's still a little bit too much, maybe. But okay, the second case, maybe just the cosmological bound becomes just stronger. Yeah, here the current cosmological bound and the standard 3-generation neutrino parameter space is end here, but the cosmological bound goes, for example, 0.05 electron volt or something like that. That can happen. Yeah. Already the current bound is 0.07 electron volts, so the 0.05 is quite near. But if it happens, then the standard 3-generation framework is excluded, but we can recover the concordance by introducing just 2 massless sterile neutrinos. That's not so radical, I think. Yeah, but anyway, what I want to say is that cosmological bounds are now a major threat to the neutrino physics, so that we, neutrino physicists, must prepare for their future attack. Yeah, that's the message, and thank you very much.
Well, I'd like to thank you again, Professor, and we are open for questions or comments.
So how can you reconcile the presence of massless sterile neutrinos with ineffective?
Ineffective. Yeah, that's super good point. And actually, the interesting thing is that, where is the bound here? Yeah, actually the ineffective, that sterile neutrino can contribute to the ineffective. Yeah, but when you introduce these interactions, then the thermal potential suppress actually the mixing between the active neutrino and the sterile neutrino in the early universe. And with that suppressed mixing, then we don't produce the sterile neutrinos in the early universe. So the bound is actually here, so that we still have the room. Yeah, naively that completely, yeah, we overproduce that sterile neutrinos, and then that is affect the ineffective, and that screw the BBN. But actually in the early universe, that mixing is suppressed because of the thermal potential made by this Z prime guy. There is a paper by Joachim Kopp and Vasudev Dasgupta about that. Yeah.
So you're saying the massless neutrinos are not abundant? They are not abundant.
Not abundant, yeah.
They are.
They are not. Yeah, they are not produced, so the mixing is suppressed in this scenario. If you introduce the sterile neutrino, just sterile neutrino in the mixing, then they will be produced. But with this interaction, there's a thermal potential in the early universe in the high temperature, then that suppresses the mixing.
No, but just the presence of the Z prime itself is already enough.
Yeah, that interaction actually is suppress the mixing. Yeah, yeah.
Thank you for your presentation. Let me ask you something. You said about the 24 sterile neutrinos. So in a real model, usually these neutrinos interact with themselves, right? So probably the heaviest will decay into the lightest. So what is the influence of the complexity of the interaction of these sterile neutrinos with themselves? Could alter these bounds?
Yeah, they are
all
massless.
Of them
yeah.
are massless.
Yes.
Oh. Strange.
Strange, yes.
Any other question?
Yeah, that's extreme.
So,
Yeah, but what I want to say is that if this situation, then just the cosmological bound goes to 0.05, and to recover the 0.06, then we only need 2. So it's not so radical.
So this does interact with the active neutrinos.
Through the mixing, yes. Yeah.
There are neutrinos from the modeling neutrino right now. So right now, what is the influence of these 24 masses sterile neutrinos?
Yeah, that's in that mixture. So they are there. Yeah, those blue ones are the massless guys, and the starting from the massive neutrinos and the active massive neutrinos, standard model neutrinos, and after that we get this. And these guys are in the universe. That's a cosmic neutrino background, and that is here the consistent with the cosmological bound. So they are there. They are there.
So they are dominant right now.
Yeah, in the cosmic neutrino background. Yeah, in this scenario.
anyone? No.
Thank you. It's curiosity. The neutrinos are the only particles related to the cosmological bounds, or the other particles can are associated to cosmological bounds?
Cosmological bound to what? To what?
To the neutrino masses. The last slide that you show is the thread of the cosmological bounds and neutrinos.
Cosmological bound to the neutrino.
He's referring to neutrinos.
Yeah.
So the only particles associated to cosmological bounds.
In this context.
In this. Okay. What's the problem? The neutrino masses or the cosmological bounds?
I don't know, but of course the cosmologists take that as the cosmology's problem. Yeah, the cosmology needs some extension, maybe. But I am particle physicist, so what I can do is maybe thinking about the particle physics model that relax the cosmological bound. So that is what. Yeah.
Okay. Thank you.
Okay, again, taking the idea from Yara. So these cosmological bounds based on cosmological simulations, they are based on a six parameter fit using CMB, H naught, spectral index, neutrino, the
lambda CDM.
Yeah, the lambda CDM, the 6 parameters. So if you do include more free parameters such as neutrino masses, you can already relax a little bit the bounds.
That's true. That's true.
If you include evolving dark energy, as you said, you relax a bit further the limits.
Yeah.
So if you introduce new non-standard interaction with the neutrinos, you can relax even further the limits.
Yeah.
So these cosmological bounds are not so robust.
That's true.
Because the lambda CDM itself is not that robust yet.
Yeah.
So, but the theory with the cosmological bounds is strict, or they relax? Yeah.
Yeah.
Okay.
Yes. So, for example, that this evolving dark energy scenario, that the cosmological, the likelihood of the neutrino mass is something like that. In the lambda CDM disk, so the bound is very strict. So that should be very small in the lambda CDM, but this evolving dark energy scenario, so the bound is weak. Yeah. So introducing more parameters in the cosmology, then we can relax the cosmological mass neutrino mass bound. That's true. Thank you very much.
I'm sorry. So now we're moving on to the next